Welcome everyone. It is my pleasure to introduce today our speaker, Dr. Bishal Deb. Dr. Bishal Deb is a postdoctoral researcher with a strong interest in enumerative combinatorics. His work focuses on the exact enumeration of combinatorial families of objects, employing projective proofs, methods, and even proofs without words to reveal elegant mathematical structure. Dr. Deb starts next week U Mathematical Science Center of Tsinghua University in Beijing as a postdoctoral researcher. Prior to this, he spent a year as a postdoctoral fellow at the Laboratoire de Probabilités, Statistique et Modélisation, Sorbonne University and University Paris City, where he was supported by the MRS grant. Dr. Deb earned his PhD from University College London in 2023 under the supervision of Professor Alain Sokal. His research entitled Enumerative Combinatorics Continued Fractions and Total Positivity explores coefficient-wise total positivity of Hankel matrices in counting problems. We are delighted to have him here today to share his insights. Please join me in welcoming Dr. Bishal Deb. Thank you again, Dr. Bishal, to accepting to be a speaker in our webinar. And please, you can start.
Okay. So let me share my screen. Yeah. So so first of all, let me begin by thanking Dr. Rafiq for inviting me to give this talk, and I'm very happy to speak at a seminar series that's named after Al-Khwarizmi, who is one of my favorite characters from the history of math. So and I will try and exhibit at least one algorithm in this during this talk. So I will be talking about, so as my title suggests, I will be introducing this notion of total positivity, especially in the context of Hankel matrices. And later during the talk, I will add the prefix coefficient-wise. So that will be coefficient-wise total positivity of Hankel matrices. And the context in which we will be discussing this is combinatorics. So let me begin. So if time permits, at the end, I will try and show some of our proof techniques and how we solve these problems. Please do not hesitate to interrupt during the talk. Yeah, so let me begin. A matrix of real numbers is said to be totally positive if all its minors are non-negative. That is, you take finite square submatrices and compute the determinants of all such finite square submatrices of this matrix. If all of these determinants are non-negative, we say that such a matrix is totally positive. Here we think of a matrix as an array of numbers and not as a linear operator. So this property is heavily basis dependent, unlike something like positive semi-definiteness, where a change of basis will still preserve the property. So here, most likely the property is not preserved when you perform a change of basis operation. Also, notice that this definition is not restricted. You don't need the matrix to be a square matrix. All we need is square submatrices to have non-negative determinants. And in fact, it need not even be a finite matrix. So in this talk, we will mostly be working with doubly infinite matrices with an infinite number of rows and an infinite number of columns. Later during the talk, we will upgrade this notion to matrices whose entries are polynomials, not just real numbers, but that will come later. So as a historical note, let me mention that this notion was independently discovered by two different groups in the 1930s. One was Krein and his school, who were studying problems in mechanics. The other was Schoenberg and his school, who were studying distribution of zeros of polynomials in the complex plane. So in this talk, we use Schoenberg's terminology. What we mean by this is, so whenever you are reading the literature on this subject, one needs to be careful what the definitions are. So different authors disagree on the definition of total positivity. So for us, totally positive matrix is one whose minors are non-negative. Let me repeat, a matrix is said to be totally positive if all its minors are non-negative, not strictly positive, non-negative. So now let me tell you what Hankel matrices are. If we have a sequence A0, A1, and so on, the infinite matrix, we construct this infinite matrix, which we call the Hankel matrix. The entry at row I and column J is A sub I plus J. So here we have A0 in the corner, A1, A1 in the off diagonal, A2, A2, A2 in the second off diagonal, and so on. And we say that this sequence is Hankel totally positive if its Hankel matrix is totally positive. And it implies, so Hankel total positivity implies that the sequence is log convex. So what log convexity means is simply you take two contiguous minors, for example, A1, A2, A2, A3, you compute the determinant. So Hankel total positivity implies in particular that A1 times A3 is bigger than or equal to A2 squared. Or more generally, AI minus 1 times AI plus 1 is bigger than or equal to AI squared. But is a lot more, implies a lot more than just log convexity. So here is a very interesting theorem that classifies, sorry, I'm just trying to remove this thing on top. Okay, yeah, so here is a very interesting theorem that classifies Hankel totally positive sequences. So for a sequence AN of real numbers, the following statements are equivalent. So the first is, of course, this sequence is Hankel totally positive, which means you take the Hankel matrix of this sequence, this matrix is totally positive. The second equivalent condition is that there exists a measure on the positive real axis, 0 infinity, such that this sequence is the sequence of moments of this measure. So it's really computing integral from, so there exists a mu, a measure mu, such that an is equal to integral 0 to infinity x power n d mu of x. And such sequence and hence such sequences are also called still just moment sequences. The third characterization is there exists a sequence of real numbers, non-negative real numbers, such that when you take the generating function, so consider this for power series, summation a n t power n, then you can write it as a continued fraction that looks like this, with these coefficients being alphas. And here you do not need to worry about convergence, because this is you want an identity at the level of formal power series, not so we do not care about convergence. More recently, there is another equivalent statement which has been added to this list. So the equivalent statement, so this says that there exists a graph G which is locally finite. So locally finite means every vertex has finitely many neighbors. It could be an infinite graph, undirected. It has a vertex, a special vertex O. All the edges have some real weights, and an is the weighted sum over all closed walks. So these are walks which start at this vertex O and come back at this vertex O, and there are two n, you traverse two n edges, you come back at O, you take the product of all the edges that you've encountered and you add all such paths, all such walks. So this is another equivalent condition. So let me pause here, and does anybody have any question at this point? Or if I can proceed.
Please, if you can repeat point 4 here.
Okay. So So here what this says is a sequence is Hankel totally positive if and only if the following also holds. So there is, if this AN is a sequence that's Hankel totally positive, then there exists some graph G. It may be infinite. It's a locally finite graph. That is to say, every vertex has finitely many neighbors. There is a vertex, a fixed vertex, a special vertex, which we call, let's say, we call it the origin vertex. And you count the number of walks that start from the origin and come back to the origin, and you take 2n edges. But then you take a weighted count, that is, you take product over the edges. Every edge has a real number that is assigned. So you take the, so you, for every such walk starting at the origin and coming back to the origin, you take product over the edges that you have in this walk, and you add all the possible walks of length 2n. Now, since this graph is locally finite, for any given length, there are only finitely many walks starting and ending at the origin. So another way of seeing it is you have a weighted version of the adjacency matrix. You can take a product, so you can multiply the adjacency matrix, take it to the power 2n, and you look at the coordinate 0, 0, and look at what that is. And so the existence of such a graph also implies that if your sequence comes from counting walks, or in summary, if your sequence comes from counting walks on a graph, then it's a still just moment sequence. Of course, counting walks from a graph that satisfies so and so conditions. Okay, so let me proceed.
May I interrupt you, please?
Yeah, sure.
If you take t equals 0, alpha 0 should be A0, no?
No, so alpha 0 should be A0, A0.
Okay.
Yeah, thank you for the question. Yes. So in fact, quite often we will assume that the sequence begins with 1. We will normalize the sequence. So A0 is 1, and then alpha 0 is 1 mostly. Okay, so let me proceed. Now, many important combinatorial sequences are still just moment sequences. So the Catalan numbers, which appear in a lot of contexts, they have the continued fraction coefficients of the Catalan numbers are 1, 1, 1, 1, 1, 1, 1. Let me go back to this slide. So here, if you put ones everywhere in this continued fraction, that will give you the Catalan numbers. So if you do not know what the Catalan numbers are, it's this they have this formula 1 over n plus 1, 2n choose n, and they are they form the moments of this measure. So this is the integral representation of the Catalan numbers. This is an integral representation of the Catalan numbers. N factorial has continued fraction coefficients 1, 1, 2, 2, 3, 3, 4, 4, and so on. So that's one way of saying that they are Hankel totally positive. But then you can also explicitly construct the measure. And so they are the moments of the exponential distribution. 2n minus 1 double factorial. So these are products of all odd numbers up to 2n minus 1. And they have continued fraction coefficients 1, 2, 3, 4, 5, 6, and so on. And they are moments of the normal distribution. So one thing I should mention is the Catalan numbers come from moments of, so they are associated to Wigner's semicircle law. 2n minus 1 double factorial comes from the normal distribution, which is associated to the usual central limit theorem. And so it seems that an n factorial comes from exponential distribution. So these sequences also seem to be associated to as moment sequences of important probability distributions. That's also one way of looking at these things. However, in this talk, I will try and do everything to avoid doing integration. So I will try and look at the other equivalent characterizations. Yes, please.
In all these cases, the entire series is diverge.
Yes.
In
Yes, that's correct.
So how you you do summation in this case if this entire series are
It's
diverge?
it's only at the level of formal power series ring. So you can formally define a power series where you do not care about and you can define division in this ring under certain conditions. So it's in the ring of formal power series. It's not in the so we really do not care about convergence. But thank you for this question. Maybe I will put a remark here that Euler was doing formal power series before, and he did not care about convergence, and that was 100 years before convergence was defined, I think. Probably by Weierstrass, if I'm not wrong, or Cauchy and others. Yeah, but anyways, we will soon look at a continued fraction of Euler as well. But thank you for the question. Okay. So let me proceed now. And here, okay, now we will look at an algorithm. So how do we guess? Suppose I'm given a sequence. I'm given the first few terms of a sequence. How can we guess whether it's Hankel totally positive or not? And here we employ an algorithm. So let A0, A1, etc. be a sequence of real numbers. You take this power series, and as formal power series, again, we do not care about convergence. As a formal power series, it satisfies this identity. And recall that this AN is Hankel totally positive. We just saw it 2 slides ago. If and only if all of these alpha naughts are non-negative. So but then as a practical question, let's say we are given the first few terms of this sequence, A0, A1 up to AN. And we want, so if we are given the first few terms, we will try and compute the first few terms of this continued fraction. And we say that if all of these coefficients are strictly positive, we guess that this sequence is Hankel totally positive. So let's see how this is done. So recall that the continued fraction coefficient started from alpha 0 and then alpha 1 and so on. But then instead let A sub j of t be the power series that is given by when you start from level j instead of level 0. So what we are looking for is actually A0, and that's the series A summation A and t power n. So we really want A0, but then we also define AJ. And recursively, we can write this. So the coefficient of alpha j plus 1 is this power series AJ plus 1. However, this is difficult to work with when you want to write it on a computer because division of power series is time consuming. Instead, here is this algorithm which actually goes back to Euler and was also later rediscovered in the early 19th century by somebody called Vyskovatov. But then more recently, a few years ago, my PhD supervisor, Alan Sokal, he was reading this paper of Euler and he reconstructed this algorithm by reworking what Euler was doing. So it's in this paper so this algorithm's been written down in this paper of Alan. So define recursively B sub j. So from A sub j, you define B sub j to be AJ times BJ minus 1. That is, BJ is AJ times AJ minus 1 times AJ minus 2 all the way up to A0. So, and let B minus 1 be 1. Then notice that BJ divided by BJ minus 1 is AJ. So the left hand side is BJ divided by BJ minus 1. And here you have alpha j, and then I'm just rewriting the identity from the previous page. Replace AJ plus 1 by BJ plus 1 divided by BJ. You reorganize the terms when you write it in this form, and you obtain something which does not involve division of power series. And then you exploit this, you write out an algorithm. You do not need to divide power series, and it works really fast. Using this algorithm, Andrew L.V. Price, so I'm copying his slide from 2 years ago. This is something he mentioned at the conference, Permutation Patterns, from 2 years ago. He ran the Euler-Vyškovatov algorithm on all the sequences which are present in the online encyclopedia of integer sequences. And he discovered that out of them, 6,719 of these seem to be still just moment sequences. And of course, epsilon, many of them have already been proved. So there was this open problem session, and he was like, okay, here is 6,000 plus open problems for this audience. So this was, so let me maybe demonstrate the algorithm quickly. So let me stop sharing and share my Mathematica notebook. Okay. So I have a Mathematica notebook. I have already the Euler-Vyškovatov algorithm, which has been implemented. And let me first do the some of the sequences I've shown you before. So for example, for n factorial, you take table n factorial, n going from 0 to 10. And I'm cheating a bit because I've already worked through this workbook before. But so here is this function, sequence to stconf frac 2. So this computes the coefficients of the continued fraction. And you see, in a very negligible amount of time, I'm computing the first few terms. So the first 10 terms of the continued fraction. But it actually works really fast. The first 1,000 terms seems to take a bit 3.5 seconds. So without Zoom running, it took 1.5 seconds. And then let's see, the first 1,500 terms can be computed within it's a bit less than 10 seconds. Mathematica has the Catalan numbers predefined, and as I told you before, the coefficients for the continued fraction for Catalan numbers is 1, 1, 1, 1, 1, 1, etc. If I take the sequence n factorial squared, that is also a still just moment sequence, you see that here these are seem to be some positive real numbers. So we guess that it's a still just moment sequence. Of course, but I mean, I cannot guess what these numbers are by looking at these numbers. Let me show you another sequence which is not a still just moment sequence. So the Fibonacci numbers are not, okay, if I take the first 4, you already get a -1 here. So you have 1, 1 and then a -1, and so it's not a still just moment sequence. It's not Hankel totally positive. However, okay, but then instead let me take the even order terms of the Fibonacci numbers, Fibonacci 2n. They are also not a still just moment sequence. You get a -1/3, so you get a negative coefficient. But then it turns out that the odd order terms are indeed a still just moment sequence. So in fact, here what happens is you get the coefficients 2, 1/2, 1/2, and 0. That is to say, it becomes a rational function. So it becomes a polynomial divided by a polynomial. So the continued fraction does not go all the way up to infinity. You hit a 0 at some point, and so it's a finite length continued fraction. And here again you have binomial coefficients, 2n choose n. The coefficients here are very similar to Catalan numbers, except you have 2 in the first term. Yeah, any questions? Okay, so let me proceed. Oh, I see there are some questions in the chat, maybe? Or
So you try to
Oh,
connect between the alpha j and the ANJ. This is your
yes,
to
yes.
connect between. But why this problem is interesting? Why?
Oh, well, it's an algorithmic question, right? I mean, if I want to understand Hankel total positivity. Now, I could construct the Hankel matrix and try and compute all the minors that I have, but it would be very computationally expensive. It will take a lot of time for the computer to go through even the first 10 cross 10, even the first 10 terms in the matrix, the computer will take a long time. But then if I take the continued fraction approach, I can verify for the first 1,000 or 1,500 terms in the sequence.
Okay, so to n positive, to n total positive, you get alpha j positive.
Yes.
Coefficient
Yes.
The converse.
Yes.
The converse.
Yes. So it's an equivalent characterization. Yes.
The converse is true if the alpha j are positive from
Yes.
starting
Yes.
from continue. You get total.
Yes, that's correct. That is correct.
Okay.
So this is the statement.
Because it's not written in the theorem. In the first theorem, it's not.
Yeah. So these conditions are equivalent.
Equivalent between the positivity to alpha j and total positivity of.
Yes, exactly.
Okay.
Yes. Okay. Yeah. Thank you for pointing this out. Yes.
Okay.
Yes. Yeah. So these conditions are equivalent. Yes. So that is, and that's the reason this is a beautiful theorem. So here, statement 1 is a statement involving matrices. Statement 2 is a statement involving measures. And statement 3, I look at it as a statement of combinatorics or formal power series. So these are statements which look, from different subjects in mathematics, let's say, but then they are all equivalent. One implies the other. Okay. So now let's upgrade this notion and take it one level higher. And let me motivate this. So the motivation is this. In combinatorics, we are often counting using polynomials, not just integers, when we want to understand a very refined quantity. So for example, the Bell polynomials, they count number of set partitions of the set 1 through n by keeping track of the number of blocks. So the coefficient of x power k in these polynomials counts the number of set partitions with k blocks. The Stirling cycle polynomials, these are the rising powers of x. The coefficient of x power k counts the number of permutations on n letters which have k cycles. The Eulerian polynomials form another example. The coefficient of x power k counts the number of permutations of n letters with k descents. So, and these polynomials, these are just very few examples, and they are studied all over combinatorics and mathematics in general. But there is no reason that we only have one single variable x. For example, you could have a bivariate polynomial x and y, where x keeps track of the number of cycles, y keeps track of the number of descents in permutations. So you could have multivariate polynomials counting several statistics simultaneously. So this motivates that instead of only considering matrices with real entries, we should also look at matrices with polynomial entries. We say that a matrix of polynomials with real coefficients is said to be coefficient-wise totally positive if all its minors, that is all square submatrices, have, and remember that the minors themselves, as they are determinants of matrices with polynomial entries, they are again going to be polynomials themselves. So the minors are all polynomials, and they are polynomials with non-negative coefficients. That is our definition of coefficient-wise total positivity. And there is no restriction on the number of variables. We can have as many variables as we want. Coefficient-wise total positivity implies point-wise total positivity. That is, if we start from a matrix which is coefficient-wise totally positive, and we substitute non-negative values to the variables of our matrix, then the resulting matrix is a matrix of real numbers which is totally positive. But it's a much stronger notion. The converse is not true. That is, if you can do this for all possible non-negative real substitutions, it need not imply that the matrix is coefficient-wise totally positive. So coefficient-wise total positivity similarly implies that this matrix satisfies, this sequence satisfies this notion called coefficient-wise log convexity. That is, Pn minus 1 times Pn plus 1 is greater than or equal to minus Pn minus Pn squared. This polynomial has all coefficients non-negative. And I recall the three equivalent characterizations which I mentioned a few slides ago. And so the natural question is, can we extend this theorem from a pointwise level to a coefficient-wise level? So can we extend this theorem to say something about polynomials rather than real numbers? And unfortunately, we cannot. Unfortunately, we do not have equivalent characterization. So instead, we have a version of, so we do not have 1 if and only if 3, for example, but we have a version of 3 implies 1 in the polynomial setting. So it does not go in the other direction. We have a version of if 3, so if we have a continued fraction of a specific form, it implies coefficient-wise Hankel total positivity. So here is this theorem due to, so this was discovered by Sokal at around 2014, but then it was really published in this large 150-page paper of Petriol, Sokal, and Zhu, which was published in Memoirs of the AMS. So if we start with, so this is the theorem. Let alphas be some variables, alpha 1, alpha 2, etc. They are all variables. So these are a sequence of indeterminates. And take this continued fraction 1 over 1 minus alpha 1t divided by 1 minus alpha 2t divided by, and so on. Take the Taylor expansion of this and extract the coefficients of t power n. And in the theory of formal power series, this is doable and it makes sense. In fact, these Sn's, they are polynomials. Sorry, just give me a moment. So in the theory, so in fact, what you obtain is that the coefficients of t power n in the Taylor expansion of this continued fraction, they form polynomials with variables alpha 1, alpha 2, alpha 3, and so on. And the theorem says that this sequence is coefficient-wise Hankel total positivity. And these polynomials are called the Stieltjes-Rogers polynomials. So in fact, this goes back to flageolet, and I will skip a proof. Maybe if we have time later, I will tell you something about the proof. But let me just quickly tell you that the proof follows from a very beautiful paper of Philip Flageolet from 1980. And to this, you add the Lindstrom-Gesell-Vienno lemma, which was also discovered, written down sometime in the 1980s. So people could have noticed this quite a while ago, but I don't think they did. I mean, it's one of those things where you tell somebody if they know both of these things, and they will immediately be like, oh yes, of course that is true, but it was never really written down until a few years ago. So if we have time later, I can show you a sketch of the proof. It's not really that difficult to tell you how this proceeds. But now the interesting thing is, if you have a continued fraction whose coefficients, if you have a continued fraction of this form, and the coefficients alpha 1, alpha 2, they are polynomials with non-negative variables, that is, you put non-negative substitutions into the alphas, it implies automatically that this sequence Sn of alpha is coefficient-wise Hankel totally positive. So let's look at a few applications of this observation. Okay, yes, and the important bit is the converse need not be true. It fails quite badly. If you start from a sequence of polynomials which seems to be coefficient-wise Hankel totally positive, the continued fraction may not be nice. So two things can happen. You could either have, most likely what can happen is these alphas will be rational functions. They won't be polynomials. They will be rational functions, and you cannot describe a nice notion of positivity on them. And the second thing that may happen is the alphas may be polynomials but could have negative coefficients. So the converse statement is not true. So you only have the statement which goes in this direction, that is coefficient-wise Hankel, existence of a nice continued fraction implies coefficient-wise Hankel total positivity. And this creates a lot of problems for us. And so it becomes really difficult when we detect coefficient-wise Hankel total positivity. If there is a continued fraction, then often it's very easy to prove, but if not, we don't know how to prove these statements. So let me, as I promised, I will, oops, sorry, I just ended up pressing the wrong button. Sorry about that. Okay, so I promised I will show you a theorem which goes back to Euler. So here it is. So in 1760, Euler discovered this continued fraction. So you take the power series, the coefficients of t power n are rising powers of x. So x times x plus 1, so on, all the way up to x plus n minus 1. And he discovered this continued fraction. The coefficients are x, 1, x plus 1, 2, x plus 2, 3, and so on. So this sequence of rising factorials, hence as a result of the theorem on the previous slide, we get that this sequence of rising powers of x, its Hankel matrix is coefficient-wise totally positive. Now here is another continued fraction. So these are the Eulerian polynomials. So the which I brushed over a while ago. But then the Eulerian numbers they count the number of permutations of n with k descents. So descent in a permutation is a position I such that sigma I is bigger than sigma I plus 1. And you take these polynomials, you add them up. Stiglitz in 1894 discovered this continued fraction. And hence, because of this existing identity, we get automatically that the Eulerian polynomials are coefficient-wise Hankel totally positive. And so the question is, how far can we take this line of work? So whenever we have a continued fraction, it automatically implies coefficient-wise Hankel totally positive. And whenever the coefficients in this continued fraction, they are non-negative. So let me tell you about, I've been talking about this particular form of a continued fraction, and these are called Stiglitz type continued fractions, but then there are also other types of continued fractions. And so again, one of the most commonly studied continued fractions. Oh, and let me mention that the terminology is different. If you're coming from a number theory background, I think the terminology is slightly different. I think these are Jacobi type continued fractions are called associated C fractions, and I think S fractions are called regular continued fractions. Anyways, so here, so previously in Stiglitz type continued fractions, you only have this linear term, whereas here you have a linear as well as a quadratic term. So continued fractions which look like this, and I do not expect you to memorize this during this talk. Let me just mention. So there are these Jacobi type continued fractions, or J fractions. Okay, I haven't gone into lattice paths, but maybe later during, if I have some time, I'll mention this. And Throne type continued fractions, or T fractions, they have this extra delta terms. And again, here, all of these are linear. And these have something to do with Schroeder paths. And S fractions, which we saw a while ago, they have something to do with Dick paths. But I haven't gone into the details there. Here is another result of Petriol, Sokal, and Zhu. And they showed that this second family here, the Throne type continued fractions, they also imply coefficient-wise Hankel total positivity. And again, similar to the situation for Stieltjes type continued fractions, the converse need not be true. Unfortunately, for the other type of continued fractions, the Jacobi type continued fractions, the existence of a J fraction does not guarantee Hankel total positivity, even for real numbers. Let me mention these continued fractions play an important role in the theory of orthogonal polynomials. So if you take, if you start, but then here is how how to handle J fractions. If you instead start from a J fraction, take its Taylor, oh, this is a typo, this should be beta gamma rather than alpha. This is a continued fraction. You take its Taylor expansion, similar to the Stieltjes type continued fraction case. You take the coefficients of t power n. You need one additional condition. The condition you need is you want this continued fraction to exist. That's the first condition. The second condition is you have this infinite tridiagonal matrix. This is the same tridiagonal matrix that occurs in the theory of orthogonal polynomials. You take ones on the superdiagonal, gammas on the diagonal, and betas on the subdiagonal. If this tridiagonal matrix, and zeros everywhere else, this is an infinite matrix. If this matrix is totally positive, it implies that this sequence of polynomials is coefficient-wise Hankel totally positive. Yes, is there a question? Okay. So I'll proceed. Now let me show some of the results that we obtain in this line of work. So the proof uses this, okay, so the proof of this result uses something called the method of production matrices. We will briefly look at that at the end. So here is let me show you the flavor of the results that we obtain in this theory. So here is this result of Alan Sokal and Zhang Zheng. They obtained this J fraction counting permutations. So what they did is they counted a large number of quantities on permutations. They took permutations, so define this polynomial. You sum over all permutations of n, and then you have all sorts of things here. You have these things cycle. I'm not defining what they are. You have these things: cycle valleys, cycle peaks, cycle double fall, cycle double rise, fixed points, crossings, nestings. And what they obtain is this continued fraction whose coefficients look like this. And you have an infinite family of coefficients, 5 infinite families of coefficients, of variables here. And so the previous theorem, what it says is, if the tridiagonal matrix, so if you make substitutions such that the tridiagonal matrix, which has ones, gammas, and betas as the diagonals, if this matrix is totally positive, if you can ensure that, then it would imply that this family of polynomials with a huge number of variables is totally positive. But then let me, so this is just to give a flavor of the kind of results that we look at. But then let me now show something I did during my PhD. there are these things called D permutations. Again, I do not expect you to read the definition, but it's there on the slides. There are these things called D permutations, and D is for Dominique Dumont. So it was introduced pretty recently by Lazar and Vox, and this was in the PhD thesis of Alex Lazar. They count a family of polynomials on 2n letters satisfying these conditions. So every even index, 2i should be bigger than or equal to sigma 2i, and 2i minus 1 should be less or equal to sigma 2i minus 1. And these numbers are called the median Genoki numbers. They look like, so let's denote them by hn plus 1. Then we again take a polynomial. I'm not going into the details here. We take a polynomial counting many different things on D permutations. And what we proved was this continued fraction, which is a thrown type continued fraction. It was this third family of continued fractions which I mentioned. And so automatically, because of the previous result, it implies that these sequences of polynomials with these A's, these letters should be bold, sorry, in infinitely many variables, this is coefficient-wise Hankel totally positive, just because we can prove this continued fraction. Let me briefly tell you about a very powerful method to prove coefficient-wise Hankel total. So I've told you how continued fractions are very important to prove Hankel total positivity. But then most often what you have is you do not have a continued fraction. If you have a continued fraction that is simple, you are lucky. But you mostly do not have a continued fraction. And one of the powerful tools that we use often is the production matrix method. And this is again a sufficient condition and not an equivalent condition. That is, existence of a production matrix implies coefficient-wise Hankel total positivity, but not in the reverse direction. Same as existence of continued fraction implied coefficient-wise Hankel total positivity, but not in the reverse direction. So let me define what a production matrix is. Let P be a doubly infinite matrix. The rows and columns are indexed by natural numbers. So this matrix, we suppose that it's row finite or column finite. That is, every row has finitely many entries which are non-zero, or that suffices, or column finite. That is, every column has finitely many entries which are non-zero. And then we define this matrix A, which we call the output matrix. So what we do is we take P power n and we look at the coefficient at row 0, column K. And one way of thinking about this is this matrix really encodes, so the production matrix is the step matrix counting walks on the natural number line. So we are counting walks which start from 0, it ends at K, and there are n steps, and if you jump from I to J, you put a weight Pij. That is what it is. And associated to these, to the production matrix method are these things called Lukasiewicz paths. So if you are familiar with them, this might be relevant. Now here is the theorem, the main theorem. If we have a production matrix P, which is coefficient-wise totally positive, what it implies is that the output matrix A is totally positive, and more importantly, the column 0 of the output matrix is Hankel total positive. And so this observation B is more important for proving coefficient-wise Hankel total positivity. So again, this gives a sufficient but far from necessary condition to prove total positivity. The existence of a Stieltjes type continued fraction is a special case of this theory of production matrices. And again, the theorem about Jacobi type continued fraction, where you have a tridiagonal matrix. So that tridiagonal matrix is actually, you can subsume it in the theory of production matrices. It's a special case. So if P is tridiagonal matrix, this Lukasiewicz paths, okay, I haven't gone into this, so let me not elaborate here. So here is our strategy. So in the kind of things we do, we use computers quite a lot to prove, to guess, first of all, guess what we need to prove. So the proofs usually consist of two steps. The first step is usually the most difficult part of the process, which is if we are given a sequence, if we have the sequence which we want to prove it's coefficient-wise totally positive, we need to guess a production matrix, and they are non-unique. They are highly non-unique. We need to guess a production matrix that is nice, and we need to prove that it is the production matrix. And then the second step is we need to prove that the production matrix is totally positive. The hardest part is usually guessing the production matrix. Once you can guess the production matrix, you can hope to do the remaining in a few years. But then if you do not know what is your production matrix, starting from scratch and guessing the production matrix is very difficult. And here is a computational, so here is a problem. So if there's someone in the audience who works with computer algebra systems, here is a problem which might interest you. So let's say we start with a sequence AN, which we want to prove it's Hankel totally positive. What we do is we put this sequence in column 0 of an infinite matrix, and the rest of the matrix is blank. We do not know what is there in the rest of the matrix. How do we fill up this matrix such that not only is this matrix totally positive, but also the production matrix of this output matrix A totally positive? So that's usually like quite hard and non-unique. So what we are doing is we have an infinite, we have one of the columns in a doubly infinite matrix. We try and guess to fill up the rest of the matrix such that it is nice. Nice meaning the production matrix is totally positive. And usually to guess this is quite hard. It's quite challenging. Let me mention that if you have the matrix, output matrix A, the production matrix is unique. So it can be computed using this simple formula where delta is, so if you have a lower triangular matrix, it's if you have an invertible lower triangular matrix, so the diagonal entries are invertible, the production matrix can be computed. So how much time do I have, by the way?
5 minutes.
Okay.
Thank you.
So here are some of the results and conjectures. So here is a conjecture on permutation patterns. So let sigma and pi be two permutations. We say that the permutation sigma contains a pattern pi if there is a subsequence of sigma that has the same relative order as pi. So we write sigma as a word. So we take sigma 1, sigma 2, sigma 3, etc. And then if there is a subsequence, sigma I1, sigma I2, sigma Ik, such that the relative order between these is the same as the permutation pi. So pi is a smaller permutation. Then we say that this permutation sigma contains this pattern pi. And this is the notation to denote the set of all permutations with n letters that avoids the pattern pi. That is, you do not contain this pattern pi. Now here is a conjecture or a general belief which was discovered by various people at around the same time from various different countries. So their conjecture is for any permutation pi, this sequence, the sequence counting the number of permutations avoiding this pattern pi, is Hankel totally positive. So it's not at the level, so this conjecture is not even at the level of coefficient-wise Hankel total positivity. So you can prove this in any of the four methods. You could either show that the Hankel matrix is totally positive, or you could construct an integral representation explicitly, or you could do something with the continued fractions, or you may construct a graph to prove this. But so far, nothing is known other than some special cases. But computationally, this seems to be true, whatever has been tried out. Here is another conjecture. So consider the number of, take n vertices and consider the number of labeled rooted trees on n vertices. So this is counted by n power n minus 1. This is Cayley's formula. And let fnk be the number of forests with k labeled trees on n vertices. So you do not just take trees, but you take forests of trees. And Alan proved in a few years ago that the sequence of polynomials is coefficient-wise Hankel totally positive. But then he also left a lot of. So what really happens when we are able to prove one of these things is coefficient-wise Hankel totally positive, is we prove maybe one result, but then we come up with 5 new conjectures or 10 new conjectures. So we are always adding a lot of conjectures to and a lot of projects to our list of things to do. So another sequence is the sequence n power n. This counts the number of functions from n to n. That is, so here n is the set 1 through n. We can represent this sequence. Okay, let me skip. But here is a conjecture. So this psi nk is the number of functional digraphs. So these are, so a function from n to n, you can consider it as a directed graph. So whenever f of I is equal to j, you draw an edge going from vertex I to vertex j. This gives you a directed graph. Let psi nk be the number of functional digraphs, this number of digraphs that has k connected components. The conjecture is this sequence of polynomials counting these functional digraphs is coefficient-wise Hankel totally positive. Here is a slide which I have copied from a talk that Alan gave at this seminar. This talk is present, like the recording is there on the internet at the Special Functions and Number Theory seminar series, and from 3 years ago. So coefficient-wise Hankel total positivity, and so let me repeat what he said in this talk. Coefficient-wise Hankel total positivity seems to be very common, but not so easy to prove. And empirically, we often find these things to be true, but we are unable to prove it because we do not have continued fractions or we do not have production matrices. And then here is a list of some of the conjectures that he presented during this talk. And we managed to prove, I mean, this first of these conjectures are roughly in increasing order of difficulty. So the first one we've managed to prove, and I think the second to the last one here, inversion enumerators for trees, this was also, I mean, Andrew L.B. Price last year managed to get very close to the proof for this. So so this was done in a paper, it was done independently, so it was first done by Baoxuan Zhu, and also me with my with some collaborators. We also have this paper which is on the archive. We managed to prove the Rook and Laguerre polynomials. So let me conclude with some final remarks. So a lot of combinatorial sequences are moment sequences. Coefficient-wise Hankel total positivity generalizes the notion of still just moment sequences, and important polynomials in combinatorics seem to be coefficient-wise Hankel totally positive. Existence of a nice continued fraction implies Hankel total positivity, but it may not exist. The production matrix is a sufficient condition to prove coefficient-wise Hankel total positivity, but it's far from necessary. And it's a big phenomenon, and we understand very little of this phenomenon. Thank you.
Thank you for you, Dr. Bishal, for this nice talk. Are there some questions, please?
Yeah, Salam alaikum.
Salam rahmatullah. Hello, Dr. Skandar. Yes,
How are you?
fine, thank you.
Thanks for this presentation. I have a remark, not question. The relation between the sequence AN and the measure mu, it is possible to find some condition in the sequence AN to such that the measure mu can be a measure probability.
Oh, yes. So the only condition that you need is the first term to be 1. So let me just... So the condition that you need is A0 should be 1. And then it's a probability measure.
Yes.
So when n equals 0, this integral should compute to 1.
When A is equal 1.
It's if it's
Yes.
that a not be given, be definite, to have a bounded measure.
Sorry?
I thought that it's if it's that a not A0 is finite. It's if it's to have a bounded measure, so we can have we can construct a probability measure.
Right, but I mean more generally, whenever a naught is any real number, I mean
Yes.
we can normalize it to make it into a probability measure.
No,
So we
non-negative.
always, almost always, non-negative probability measure. Yes. Yes, a non-negative real number. Yes, we can normalize it, and it will be a probability measure. Thank you.
Yeah, and in this case can be explicit the measure mu, because in this case n is the derivation of characteristic function of mu.
So that's more tricky to answer. You may not always be able to construct the measure explicitly. I mean, or at least we do not know how to do it always. I know a technique where you can do it when this formal power series, summation ant power n, it satisfies a polynomial equation. That is to say, it's an algebraic sequence. But other than that, it's hard to so if I understand what you're saying is, if I start from this sequence of moments, can I construct the measure? I think that is hard. And so we try to do everything to avoid that.
The answer is not yes for in all cases. If you have
It's
the
difficult.
moments,
It's difficult.
not difficult, but we can. The measure is not characterized by the moments.
Sorry, are you still there?
Only,
Sorry, I think I missed. Maybe it's my internet connection.
yes.
Can you please repeat?
Okay. The moments not
What about
characterized.
the unicity, you mean?
Yes, you have not the unicity in all cases. There are some special cases where the moments characterize the distribution.
Yes. So I think this forms a small part of a much larger story on the moment problem, and there's a book on this. And I think there are some conditions which imply unicity of the measure, but yeah, I won't be able to tell you more on this right now.
The Kalman conditions, probably you mean.
Yes.
Yes. Thank you.
And you're setting on globe everything about what we call the Hamburger sequences are more general, right?
Yes. Yes. So the hamburger moment sequences, thank you for asking this. So they, instead of the positive real axis, they are defined on the entire real line. So from minus infinity to infinity.
And then what you said applies to the Hausdorff, no? Sequences.
Hausdorff is 0 and 1.
0 and 1.
Yes.
And
yes,
you have
yes. So
the same characterization, or what differs? What is the difference?
So for Hausdorff moment sequences, so for hamburger moment sequence, they are characterized by the existence of a Jacobi type continued fraction. This is a Stieltjes type continued fraction.
Okay.
They're characterized by, let me go a bit further. So hamburger moment sequences are characterized, they exist if and only if you have a Jacobi type continued fraction that looks like this.
With the square, okay, appearing. And for Hausdorff, it will be easier, more compact.
So for the
For the Hausdorff, it will be easier, no?
Yes. So for Hausdorff moment sequences, you have a Stieltjes type continued fraction. So a continued fraction that looks like this. But then you also have some coefficients satisfy.
Dr. Bishal, you have a problem with the net, I think.
Hi. Oh, sorry. I think, was it my internet?
Yes, your internet, yes.
Oh, sorry about that.
Please, if you can share again. If you can share again the slides. Yeah. Okay. Okay, thank you.
So the Hausdorff moment sequences, since they are a special case of Stieltjes moment sequences, you have an S fraction, but then now the alphas should satisfy certain conditions. So they aren't just non-negative. I think you also have an. Now I'm forgetting what the exact condition was, but the alphas also satisfy a condition.
Okay, a more restrictive condition, probably.
Yes. So there is an upper bound as well.
Please, slide 44. Slide 44, please.
Okay.
Okay. What is the difference between the theorem and the conjecture? For me, it seems the same. Same.
Right. So the theorem is about number of trees. You're counting trees and
okay.
So if you put x equals 1, you will get n power n minus 1 in the theorem.
Yes.
If you put x equals 1, you will get n power n in the conjecture.
Okay. Mm-hmm.
So these are different objects, but you're absolutely right. The sort of statement is similar. So the first statement, you're counting forests with labeled trees, and in the conjecture, you're not counting forests. You're counting functional digraphs.
Okay. Other questions, please. Okay. Now we have to thank again Dr. Bishal for this nice talk and nice topics. And see you after 2 weeks with our next speaker, Jean Bertoin, which gives a talk about the branching process. So see you after 2 weeks. Thank you, Dr. Bishal. Thank you very much.
Thank you very much.
Thank you.